glad to see you all on my JCON session. Today, we speak about downsizing and how to make Java containers lightweight. So here we go. Several words about me and my background. My name is Mike, and I am working in IT over 18 years, mostly in backend development. Today, I represent Deutsche Bank Technology Center, where I'm currently working as a lead Java developer in a platform team. We create solutions for internal use, which are subsequently used by a large number of business teams. Applications have a long history, most of them fall into low latency category, which means there is a heavy emphasis on high availability and imposes, I think, certain restrictions on the architecture on both the applications themselves and the environment in which they operate. So we will speak from this perspective. And we'll talk about the problem of the explosive growth of the storage space consumption of Docker images. And discuss also how it could be solved for Java-based application. First, we will dive into the problem, answering why it is important and where it comes from. Then we will look at the existing approaches and finally get into the new idea, what is it and how it helps. And at the end of the session, we'll discuss what's pros and cons of it, and I can answer your questions. Yeah. So let's talk about the root causes of the problem. At first, let's look at the enterprise environment we have to work in. You'd expect around 1,000 teams working with more than 500 microservices. Each team produces a lot of business and platform code, and finally they meet in production where they must place the components in a consistent manner. That's the challenge for every big company. The infrastructure must be able to withstand heavy loads, especially during release deployment. I should note that here and after we will talk about Kubernetes or another similar image-based deployment management system. So, as you know, each microservice has to be packed into image and deployed to cluster. Let's do simple calculations. Typical size of Java-based application, I think, is around 200 megabytes. Assume average number of microservices per team is 5. So we obtain 1 gigabyte of bundled applications from each team. These bundles come to binary repository. So if we have 100 teams in a company, it means only one release holds over 100 gigabytes of storage space. Having at least one release a week, we will grow up to 500 gigabytes per month. And I didn't talk yet about mid-week releases and environment for developers, where loads could be much higher. So we have a problem with image storage size, but the same is true for the time and network throughputs required to deploy the application. All these images finally go to cluster nodes, so you can end up with network traffic issues. All that means decreasing of service availability and high recovery time. So nearly each team works independently on the microservice, and developers could design its own public API, define it, for example, in OpenAPI specification, implement, test, deploy in production, and so on. And they could do it without any coordination with other teams. This is the main idea of microservice architecture. But sometimes this ideal world gives a crack. What if we have to work with common data model, which cannot be split without significant effort, or even cannot be split at all? Or maybe you have some critical low latency algorithm and want to share it without getting started a new microservice. Everybody who worked in enterprise environment knows it's a common practice to have a lot of such code. And the situation could be even worse if you have, for example, a legacy code base from monolith applications. So, of course, from the point of view of microservice architecture, it's better to avoid shared libraries. But in real life, it's not always possible. And even if it is possible, it's not the best solution. It might be not the best solution. Sometimes it is better to have tight coupling and avoid a lot of boilerplate code to remove unwanted latency, for example, between microservices. So we can state the fact that from one side, we strive to build microservice architecture that could allow teams to work independently. And from the other side, we may have a lot of common code base. Can be Java itself, common frameworks, like, for example, Spring, a legacy code base from monolith applications, common data model, shared algorithms, and off top of this stack, we have our application and in project libraries. In project, I mean that libraries that comes from applications modules in terms, for example, of Maven. So all these dependencies could be split into three large groups. First of all, Java itself and common frameworks are called platform libraries. Shared algorithms, common data model, and legacy code base are called external, and apps itself is some kind of internal binaries. What of these groups is more significant in terms of bundle size? I got, for instance, one of my projects I have worked on and calculated the size of each library group. On the table, you can see that almost 50% of application bundle is used by external libraries. Java took only 43%, and app itself with internal libraries requires only 6%. And the rest of the space has gone to external platform. But situation is even worse because the real usage of classes coming from the external dependencies is really very poor. In my case, over 50% of jars doesn't contain classes loaded during execution. This one, It means they included in the application bundle mostly because of non-class resources, and context, for example, declarations. And another 50%, I think, is not better because only 10% of classes inside these jars are really loaded during lifetime. So we have over 90% of classes that are not loaded at all. This is the very degree of compression to which I think we need to strive. And of course, the problem is multiplied by life cycle of the groups. Most frequent changes comes from the internal and external libraries, while platform libraries represent the most stable part of the application. But it also could be a part of the problem if you have, for example, several versions of platform dependencies. Anyway, the vast majority of the problems comes from the second group with external dependencies. They are updated frequently, managed by different teams with its own life cycle, and could be included in different versions and combinations by different microservices. So we have looked at the problem from different angles and understand where the problem comes from. So let's look at what ways there are to solve a problem in Java world. What's good and bad about each of them, and why we might need to invent something new. There are several existing solutions I could find, and that could help to reduce the size of the image. The first one is strict dependency management. The next is layered images and native compilation. The last but not least. So, strict dependency management, what does it mean? Oh, sorry. Something went wrong. I need to roll back my mouse. What's happened? Okay. So, as I already said, even platform dependencies could be an issue of the problem. If you didn't pay attention to dependency management, if you have monorepo, you can use root pom to define all libraries in dependency management section. For multi-repo, you could use bill of material for the same goal. This is primarily about the purity of the code, which is always good in itself, but I think it is often lacking in enterprise development. But of course, this is not always a pleasant and easy process. Monitoring the state of the code is a must and should be done by all developers on all teams. As soon as at least one team appeared to does not follow the general rules, the house of cards collapses. So a system that uses only this approach become, I think, unstable, and over time it returns to its natural state with a high entropy of dependencies. So that's why we are going further for the next approach is native compilation. The idea is to calculate and remove from bundle all classes and resources that are not needed when the application runs. And do this on compilation phase, knowing in advance what exactly we need, we literally achieve the maximum 10-fold optimization of the bundle size. And as you may know, an example of the implementation of this approach is a GraalVM native images. But even in this case, there are pitfalls. Let's touch them quickly, just to understand why we need yet another solution. So reflection, dynamic class loading, dynamic class proxies, and so on have to be configured manually. Application class path is static and can be changed. Not a big problem for those who sits in container, but I think it might be still relevant in some cases. So what we can say else, lazy class loading is not supported. And of course, it still contains duplicated data. Yep. For instance, if you have several microservices that use the same library, you will have several copies of the same classes in different images. Yep, you may think that the size is quite good, but don't worry, I have something better. Anyway, a native compilation is a good solution if you can use it. So next slide about layered images, the third solution. What we know about layers? We know that images are actually made of several layers, each of which has its own unique hash code. I placed an example of bundle. You can see here several layers with their own unique hash codes. And when image engine loads them from repository. It could be Docker or some analogs. It first check whether the layers requested in the application image already exists on the node. And only those that do not yet exist will be really downloaded. Armed with this tool, let's see what layers a Java application can be divided into to minimize data loading by reusing the same layers. On our dependency type diagram, we could split them like into 3 layers. This is a rough division. In fact, there may be more layers. We probably won't encounter problem in either the first and the third layers, but we are primarily interested in the intermediate layer with external libraries. Because different applications require different sets of libraries. So the hash code for each for this layer will be always different, and we really want to optimize the image size through reuse of these layers. I think more precisely, we are not so much struggling with the size of the image on this approach, as we are trying to do labor-intensive image downloads as rarely as possible, leaving the problem of storage space behind. So anyway, how could we organize the intermediate layers with external libraries? Since we want to reuse layers as much as possible, we should, at the limit, place each external library on a separate layer. However, this looks terrible even in theory, but in practice, it will turn into a nightmare. It's simply impossible to manage such setup. However, you can try to find some solution where you can group some libraries into layers according to, for example, common feature. But anyway, it's also a very complex organizational task with a temporary effect, because after a couple of releases, new dependencies will appear, and they will be included in some existing layer, and finally, entropy will increase again. Besides that, we need a two-step process in this approach. First, we need to analyze dependencies across all projects or modules to get a full list of them. And only then we need to build application images moving external libraries to separate layers. It can be complicated because you need to go to all your teams to collect these dependencies. So we have, of course, a lot of cons, two-step process for collecting, complicated project dependency management. I forgot to say about number of layers. It's also limited up to 128 layers, so you cannot increase it unlimited. And of course, we end up with uncontrollable Docker wrapper growth because we produce new layers. So I think this is the very moment when you should stop and think whether we are solving the right problem and whether there is a simple solution, if you haven't fallen asleep yet. So let's talk about green containers. So let's return to our diagram with layers and groups of libraries. And I thought, if I can't use layers for external libraries efficiently, can I skip this layer at all? But if I skip this layer, where can I get external dependencies? And the answer could be quite obvious. Everybody knows that we already have a space for all dependencies like Nexus or what you want. So why not to use it directly? So my idea is to use the artifact repository as is, but instead of downloading the dependencies and placing them in the image during the build phase, we'll postpone it to the later phase of the container's life cycle. And that's why container becomes lightweight and green, as I call it. The only layer it has, except of course base Java image, is the application itself and a list of dependencies. And note that by happy coincidence, we already have class path file, so we do not need to invent everything new. We just need to use it in a new way. This is how it looks. We left only two layers. The first layer contains Java, common frameworks, and some stable libraries. Of course, you can remove them as well. Anyway, it doesn't matter. And on the second layer, we have application, some list of external libraries, and our binary repository that we reference to from this list. So what steps do we need to implement this approach? First of all, we need to build the application as usual and remove external dependencies. Then we need to build container with class path file. And before running application, we need to download dependencies from repository to the container. After that, we can start our application. To create images of Java application, we are using, and it is very convenient to use, JIB plugin. In my case, for a sample application, it produced quite big image, around 400 megabytes. And fortunately, JIB Maven plugin allows you to write your own extensions that can radically change the process of building the image. We took advantage of this and wrote our own extension that does three simple things. It determines external dependencies, removes them from the layer, and generates instead a list of external dependencies to be loaded later. With this extension in this plugin, image size became around 70 megabytes. I think good, but I have more good news. This is actually the size of a basic layer where Java core lives. So here I placed some screenshots with a comparison what was and what comes with such approach. You can see that at least two layers, this and this one, we shrink it significantly, and instead of almost 400 megabytes, we have only 1.2 megabytes for these topmost layers, and that is of course 300 times less than we have previously. And 68 megabytes is for basic layers. But we still need to answer some questions how to implement it. And first, let's talk about class path file I will mention before, and talk how it might be helpful in our case. The practice of using such a file shows that its format can be adopted and for loading external dependencies. On the screenshot, I placed an example of this file. your format can be the same or different, doesn't matter, but all external dependencies must be listed explicitly. And now the final ingredient, loading. And here I can offer you two options. The first primitive option is to download dependencies right into the container. You need some empty volume mounted to the container and some kind of run script, which you could fire an application startup right before Java command. So how it works? On the first phase, run script goes to binary repository with your external dependencies and download all jars listed in class path config. And of course, it stores it to empty dir volume. And the second step is to run application itself, passing the class path as part of the Java command, as I shown previously. I think the solution is pretty straightforward and easy to implement and support, but it still have several problems we should address before production use. As you can see, download is fired for every instance of every microservice. This solution looks traffic unfriendly. Therefore, it has all disadvantages like slow recovery and not the space consumption, because you download the same libraries into the same node several times. And if you have 100, for example, instances on the node, you will download some common libraries 100 times. It's obvious that it's not good. So how could we improve our solution? You can see pros and cons. Yep. And an answer finally comes with a custom operator and preheating cluster nodes with external dependencies. So on the build phase, we create a custom resource definition that describes all the dependencies needed for application. It comes from our class path file, and what does it mean? It, for example, contain a list of dependencies with their versions. It contain reference to application itself, and of course its version as well. So you can determine what custom resource belongs to. So release operator, what does it do? It watches for changes of the custom resources definitions in our Kubernetes cluster and synchronizes them with the cluster nodes. It downloads dependencies in advance and places them into the special sync folder on each node, this one. So when the container starts, it just mounts the volume and starts the application. No additional actions are required, and the application starts as usual. The only difference is that it does not contain the external libraries, and they are placed outside in the volume and shared between all containers. It's very important for us that we do not download these dependencies twice. And what does it mean? For example, if your application fails, Kubernetes cluster will move it to another node. And in case if we have preheated environment with all needed data, it will start very quickly. You do not need to download additional layers from application images if it was not downloaded previously. So I think we made the final significant improvement. So we have a lot of pros, but of course, several cons. Preheated nodes contains of all needed dependencies, fast startup time, quite simple dependency management, small image size, and of course, all advantages of dynamic and dynamic class loading and resource loading that we had no in native image compilation. From the other hand, we have several cons. It mostly comes from the core of idea that we need some kind of plugin to analyze project dependencies and need some kind of custom Kubernetes operator to manage all these dependencies. I think in some companies it might be difficult to support and should be allowed by security teams. So I just place these bullets here. But we have no such problems in our company. And the only thing we need to do is just to develop our plugin and operator. So, and the last slide, I tried to accumulate all pros and cons of the solution. Strict dependency management, sorry, looks a bit confusing because it could be a part of any other approaches, but I decided to mention it here. Anyway, I have 3 marks: high, low, and middle. And I think we have at least 2 winners: native compilation and green containers. But as you know, native compilation is not always possible. So that is the reason why we use green containers in our company as the best solution for us. It still requires some effort to implement JIP extension operator, but it was done once, and then you can use it for all your microservices. So thank you for your attention. I hope you enjoyed my session, and I'm ready to answer your questions. We have almost 10 or 15 maybe minutes. I need to stop presentation. So, guys, do you have any questions? I see some messages in chat. Let's go through it.
Do you want me to read them out?
No. Oh, yeah, of course I can read it. How did you know which classes got loaded and which not? Is there any utility for that? This task is done by a JIP plugin. So regularly it scans all dependencies, and if this exact dependency do not belong to project itself, it is treated as external. So the list is prepared very simple, just with one scan. The whole idea implies that all teams and all services are on the same versions of libraries, right? No, because we don't worry about versions at all. We just use our binary repository and download exactly that libraries that were requested to be in application. You can download several versions of the same library, and it is okay. You can treat it as, for example, Maven repository you hold on local machine. But it's not a Maven repository because it holds only those libraries that are really needed for application. Is there any other way to remove unused classes beside native compilation? I know there is some kind of plugin for Java application that could remove it. And we even play with it, but it has a problem. The same problem as when you have a native compilation of your Java application, because you need to predict somehow what libraries could be loaded in runtime. If you do not have such information, application could break during in production. So it's not a good idea. So we do not get into this solution. Yes, ProgWard. Yes. What do you think of Quarkus to address the problem of Java upsize? I think it's just another solution. Maybe it should be on my presentation as well. But the idea is to use you can use green containers with any platforms you like. It doesn't matter what kind of basic frameworks do you really use. So if you can use Quarkus, it's okay. If you cannot, sorry, you can go to green containers. So did you evaluate GRE modules? Sorry, do not understand the real question, because we are talking about a lot of external dependencies that comes from our teams. So maybe you can clarify your question. Okay, how will upgrade actually work? Spring Boot, as the same. If you upgrade Spring Boot, it could be external library, or if you left it in the basic layer, so your basic layer will be updated, of course, and then you will download it during application startup. But we are struggling with downloads that occurs very often, and you can ask yourself how much times do I upgrade Spring Boot from one version to another, and the answer comes that I think twice a year maybe. So it's not a problem at all. But when you need to use some dependencies from the other teams, the life cycle of such dependencies is, for example, once a week. So it's much more bigger problem than Spring Boot. What do we need? We need to upgrade all the services first, and for all an update, we would have to both version of ClassPass. Yes, but I think it's possible. Anyway, you can exclude Spring Boot as well and load it with green containers idea. What's about to use a deduplicating file system to store the individual container images? Yes, you can. You can do it, but for example, if you go into some public cloud like Google Cloud or Amazon or Microsoft, I don't think you have such option. So we are operating on much more higher level that deduplicating file system, and it works well.